This video is for Lesson 10 in Unit 4. It's our second day of related rates. And we're going to do kind of more of what we were doing last day, more of the same. But this time, we're going to tolerate and actually be pretty happy having multiple variables going on, perhaps on the right-hand side of the equation. And we'll end up just using the product rule as we're going through our work. So you're going to notice, kind of going back, a whole chapter here, to, if you have y is equal to some algebra multiplied by some algebra, and you go to do a derivative, it'll be time derivatives today, but you could do the derivative of the first thing multiplied by the other thing left alone, and then you would switch gears and then do the derivative of the second thing. And that's going to be what's happening in this story. We're going to have multiple things on the right-hand side, and they might both be changing independently, right? So two things changing, and changing kind of in their own way, doing their own thing. So what do we got here for the note? Sometimes more than two quantities are changing within a certain relationship. At this point, you must consider the product rule, the quotient rule, and the chain rule when differentiating to express how the different rates are related together. Yeah, you bet. Okay, so some practice on this page, and then actually just 3 quick examples. They'd be done fairly fast here for this lesson. A rectangle, the area is equal to length times width. Well, what happens if you've got a rectangle like this one and it's changing? Like maybe the length is growing and maybe the width is growing too, but maybe not like this, maybe not proportionally. Maybe the length is growing quite quickly and the width is growing, just a little bit, right? Or maybe actually like one is growing and the other one is shrinking, right? Like that can happen. So we're going to be ready to do any of those stories just by doing the product rule. So if this is the equation, A is equal to length times width, then if I was to do my related rates, I could say, hey, dA dt, the speed at which the area is changing, it's equal to, I'll do my first derivative here, I'll say dL dt, the speed at which the length changes, multiplied by the width left alone, plus, leave the length, and then dW dt. There you go. We've just tied those things together. What about a triangle? Well, it's got a 1/2 in there, but I can just group that 1/2 with the b, no big deal, and say, oh, okay, dA dt is equal to, my first derivative here would be 1/2, and then dB dt multiplied by h, and then add 1/2 b multiplied by dH dt. And what I've done is I've got ties now between this rate and this rate and this rate, like 3 different rates going on in this story, and I can see how they're all tied together. You could have a right angle triangle that's actually totally morphing. It might be morphing in a non-proportional way, right? So maybe I'll just draw a little triangle here, a little right angle triangle, right? Might look like this. Maybe it's growing this way, but shrinking this way. And we're going to be able to figure out how all that ties together with the hypotenuse. And we could just do a time derivative of everything. So if I do a time derivative over here on the left-hand side, I would do a lot of cheating with the chain rule. And I might say, okay, let's cheat first. X squared can become 2x, but that was cheating. So I multiply by dx dt. Moving on. We'll cheat, we'll do a y derivative, 2y. Oh, but then we'll fix it by going dy dt is equal to, this could be your hypotenuse here. We'll cheat, we'll do a z derivative, 2z, and then multiplied by dz dt. And once again, I've got 3 different rates. The rate at which that leg of the triangle changes, the rate at which that leg of the triangle changes, and the rate at which the hypotenuse changes. And I can see now how they're all nicely tied together. For a cylinder, if I wanted to imagine a cylinder that was morphing as time goes by, right? So again, the cylinder kind of looks like this, but maybe it's getting wider but shorter, right? It could be doing anything. Those variables can be changing independently, and we're going to be able to relate the rates together just with doing a time derivative. So here I would say, okay, on the left-hand side, I'll end up with dV dt. Now, moving on, I might group the pi with the r squared and say, okay, the first derivative here, I'll cheat. I'll do an r derivative and say, okay, 2 pi r, but that was cheating. So I have to multiply by a dr dt. But that's just the derivative of the first factor. So now I still have to go and multiply by h. And then moving down the road, pi r squared times dh dt. Make sure you include this h here. A lot of people forget about that because they know that they have to do a little extra work with this chain rule, and that's great, but then they forget that, yeah, you're in the middle of a product rule, right? There's still some stuff to go. We'll practice that again right here when we go to look at a cone. So for this cone story, maybe I'll group the 1/3 with the pi r squared. And so I have to remember that I'm in the middle of a product rule. And I could say dv dt, I'm doing a time derivative. Okay, here comes the first cheat here with a chain rule. I would say 2/3 pi times r, and then times dr dt. Well, that's just the derivative. That's the derivative of the stuff in the blue brackets. Then times h, often forgotten. Then switching it around. Leave the 1/3 pi r squared times dh dt. Okay, so that's the setup. Now let's go and give this a try with 3 examples. First one here, I'm going to fill up a cone full of gravel. That's some sort of gravel pit. It says, gravel is being dumped from a conveyor belt onto the top of an ever-increasing cone pile. At the moment when the diameter of the cone is 8 meters, the height of the cone is 12, the diameter is increasing at a rate of 0.5 meters per minute, height's increasing at 1.25. Lots of stuff going on here, and they want to know at what rate in meters cubed per minute is the gravel being dumped onto the pile. Okay, well let's get comfortable with our picture here. Got a pile of gravel, right? It looks like a cone. Let's draw that. It's at a gravel pit. Okay, there it is. Big pile of gravel that's got some height to it, and it's got some radius to it, and both of those things are changing. And they're changing because somebody's got a conveyor belt here, and they're dumping more and more gravel onto this pile, right? So gravel's coming up the conveyor belt, and it's going zoop, and then landing onto this pile. Okay, well, I want to tie everything together. The volume and the R and the H, no problem. I could go with the equation for a cone. V is equal to 1/3 pi r squared times h. So that's going to tie those 3 things together: volume, radius, and height. Okay, let's go and do a t derivative. So if I do a time derivative, I'm going to end up with dv dt is equal to, now I'm going to group it like that. I think that will work well. So I'm going to have to do the product rule, and while I'm doing this product rule, the chain rule is going to show up in there at the same time. So my first factor in the product rule, doing a time derivative. I'm going to cheat and do an r derivative for a second, and I get 2/3 pi times r. But that was cheating. I treated that like an r derivative. I should have done a t derivative, so I'll just fix this here. dr dt. Okay, that's the derivative of the first thing. Now I have to multiply it by the other thing left alone. Then, moving on down the road, leave the first factor, multiplied by the derivative of the second thing. I'm supposed to be doing these t derivatives, right? So that looks fair. All right, now it's time to go and put some information in. And it looks like at this instant, we've got some information. Okay, this one little moment we're trying to catch. It looks like they're telling us that the height at this one moment, just reading through the problem here, the height's going to be 12. And then the speed at which the height is changing, the dh dt, now they've told me that there is 1.25. Okay, that's great. Now they told me about diameter. Well, that's no fun, but I do know this, that the radius is just half the diameter. So whatever they tell me about the diameter, I can cut everything in half. So when they said, oh yeah, at this moment the diameter is 8. Okay, well at this moment then I guess the radius is 4. And even the speed at which things change, because the radius is half the diameter, it's going to be growing at half the rate. So when they said, oh yeah, the diameter there, it's actually, what did they say? The diameter is increasing at a rate of 0.5. Okay, well then this would be half of that. That would be 0.25. Okay, it's time to go and substitute all that information in. I've got my transient numbers ready to roll. Calculus is done. And I can go and figure out exactly what that dV dt is. That's what they wanted me to do, right? Find the rate at which the gravel is being dumped onto the pile. Okay, perfect. dV dt is equal to, now it's just plug and play, 2/3 times pi times 4 times 0.25 times the height, don't forget about that, 12, plus 1/3 pi, and then the radius, 4, it gets squared, and then the dHdt, 1.25. Now, personally, I kind of like it if I can come up with some nice clean answers. I know we've talked about this before, but I'll just demonstrate this for you again. I might go and grab my calculator, and I might just avoid putting in the pi's, just to see what it looks like. So I'd be sitting there going, okay, 2/3 times a 4 times 0.25 times the 12, add on, and again, 1/3, don't put the pi in, 1/3 times 4 squared times 1.25. This might look fairly clean. Okay, well that looks like some sort of third thing, right? In fact, how many thirds is that? 44 thirds. Okay, so it's just a little bit nicer looking to say, oh, okay, how about an answer of 44 thirds pi, right? There comes the pi. And then the units would be meters cubed per minute. If you were a little bit bothered by me saying, well, hey, the radius is going to be changing at half the rate the diameter is changing, you could have done a whole new related rates question. You could have said, okay, I've got my diameter, and it's equal to twice the radius. And if I do a chain rule here, or well, chain rule and just related rates in general, I could say d dt is equal to, do an r derivative here, 2, and then dr dt, there it is. I can see that the dr dt is going to be half as big as the dd dt, the rate at which the diameter is changing. Okay, so that's that one. We had that cone pile that was kind of morphing. The next one's going to be the story about somebody on a ladder that slides down a wall because somebody wasn't holding the ladder down the bottom. Suppose a story here, say we've got a 10-meter long ladder leaning against a building, and the bottom begins to slide out. The bottom slides outwards at a constant rate of 2.5. How fast is the top of the ladder falling? So we're kind of worried about, like right here, the very top of the ladder, how fast is it going down at different times when the base is 6 meters away, 9.5, and then 10 meters away. Well, I don't mind putting in the 10 for how long the ladder is, but don't lock in how far the ladder is from the wall or how far it is up from the floor. Instead, let's keep that floating, right? So maybe I'll call this y. And we can call this x going this way. And that way my calculus can have a chance to dive into this problem. The 10, though, is locked in. That's never going to change. So we've done one kind of like this before with the police car, but here's just another way to look at it. X squared plus y squared is equal to, well, it'll be 10 squared. So it's going to be 100. And I could go and do my calculus. I could go and do a t derivative. And I would end up with 2x times dx dt plus 2y times dy dt, so I'm doing chain rule along the way here, is equal to 0. And it looks like they want to know this velocity. How fast is the tip of the ladder falling down? So if you're up at the tip, how fast are you dropping as that ladder begins to slide away? Well, we can rearrange this a little bit. Right? If we start solving for that, we could say, well, for starters, let's get rid of these 2's. We really don't need them, right? So they're gone. And then making this a little bit better, we could say y times dy dt is equal to negative x times dx dt. Okay. totally solving for dy dt because they're asking me some questions about it. How fast is that falling? I'm going to have to divide by the y. Looks like I'm going to end up with negative x divided by y times dx dt. Now that's great, that works, but I've noticed up in the story here, they're going to ask me a whole bunch of questions, and every time they want to tell me the value for x, right? So all of these are going to be some nice transient x values, and they don't tell me what the y is. So maybe I'll just use that Pythagoras equation there that's in black, and let's modify this calculus so that we're ready to do this quickly. We could write this as a negative x divided by, now instead of saying y, I could actually put in here just that Pythagoras reworked. It would be 100 minus x squared. So all I've done, if you're wondering, okay, whoa, where'd that come from? I just took this, just solve for y, and said, hey, look, I'm going to need to solve for y quickly here, so why don't I just rearrange this, make it all ready to go. So there's my negative x on top of y, and then I'm going to multiply that by the dx dt, which is how fast the foot of the ladder is actually sliding out. Well, they've actually got 3 ones that we want to go and check, so this should go pretty quick. First story is when x is equal to 6. Okay, so the foot of the ladder, the heel of the ladder is 6 meters away, and we're going to find out what dy dt is. So I'd go, okay, great, here goes. Dy dt is equal to, it's going to be negative 6, just negative x value, and then a little Pythagoras here to figure out how far we are away. That'd be 100 minus 6 squared, that'll figure out the y, times dx dt. Well, they said it was sliding away at 2.5, that was its velocity. Now I tried this out, and I'll just offer you the answer because I just want to compare answers as opposed to having you spend a lot of time working this all out. I had that number. The units would be whatever you're measuring y in, which is meters, divided by whatever you're measuring time in, which would be seconds. Now watch what happens as you get farther away from the wall. What about when the heel of the ladder is 9.5 meters away from the wall? It's almost fully fallen down. But if you keep pulling the base of the ladder away at 2.5 meters per second, here's what ends up happening. You'd have a negative 9.5. Okay, that's a little bigger. But then this denominator starts to do crazy things. You'd have the square root of 100 minus 9.5 squared. It's getting awfully small in that denominator. And then multiplied by 2.5. And this velocity is much, much bigger. Negative 7.6060 meters per second. Okay, well, I'm going to have to scrunch that up to get it to fit. I can do that. There we go. Okay, one more. What about the instant, mathematically anyways, when the tip of the ladder is basically at the ground? That's what this last story is. What about when x is 10 and the ladder is just about on the ground? Then when you go and do the dy dt, you get some really interesting math. You'd have in the top a negative 10, okay, not all that interesting. But then this denominator would be 100 minus 10 squared times 2.5. Well, you're going to get division by 0. So essentially, if you think about it as a limit here, it's going to minus infinity. So the tip of the ladder is now dropping faster than the speed of light, right? And that would have to be the case mathematically in order to keep the heel of the ladder, the bottom of the ladder, sliding away at 2.5 meters per second. Now, obviously, the physics is going to say, hey, ladders, even tips of ladders can't move faster than the speed of light. And the ladder would start to twist, right? It wouldn't actually be a rigid body anymore. But it's kind of neat what the math is doing there. Now, one last question. This one here, a little story about a police chase. So it says a police cruiser is approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner already and is now moving straight east. When the cruiser is 0.6 miles north of the intersection, the car it's chasing is 0.8 miles to the east of the intersection, and the police determine with radar that the distance between them and the car, the speeding car, is increasing at 20 miles per hour. Now the police car is moving at 60 miles per hour. You have to figure out the speed of the car. So you're like some sort of calculus forensics person here trying to figure out how fast they're actually going. So I need to draw myself an intersection so I can get comfortable here. So there's one road. Ooh, get my pen to work. Hang on 1 second. Okay, I think I got it working here now. There we go. So there's one road. Here's the other road. And I've got these two cars. So I'm just going to draw these cars in. Now remember, they're moving, so I don't want to lock their distances in. Here's the police car. It's coming in from the north. All right, we'll put some little lights on here. Okay, so they're traveling code 3 with their lights on. And then the speeding car has already turned the corner and is heading east, so they're out here going this way. Now, I know the story says, oh yeah, the police car is 0.6 miles away, right? But don't do that. And the speeding car is 0.8 miles away. Don't do that. Because if you do, then those cars are parked and it's no longer a police chase. So instead, what I want to do is come up with a variable for this. Like, I don't know why. And a variable for how far the speeding car is away. Like, I don't know, X. And then there's talk about like radar ranging between those two vehicles. Like you're measuring the speed at which a rope would be growing. So maybe I'll call that R. Okay. Well, let's go and think about some equation that's going to tie all of that together. And I'm thinking Pythagoras. How about x squared plus y squared is equal to r squared? Time to do a derivative. So here comes the calculus. I'm going to cheat with a chain rule like crazy here. 2x times dx dt plus 2y times dy dt is equal to 2r times dr dt. Now what we want to know is how fast is that speeding car actually leaving the scene, right? So the speeder is here. We want to know this. That would be their velocity. So we're going to need everything else. Well, we don't need these 2's. There are 2's in every term, so gone, gone, gone. But let's see if we're ready to go. Do we know, now that the calculus is finished and we're putting in transients, do we know the x? Yes, that's a 0.8. We're looking for dx dt. Do we know the y? Yeah, that's 0.6. The dy dt, that's going to be the speed of the police car. We've got that one. And dr dt, we know that one. That's what the radar gun is showing. Oh, the r. We have to go find that. So we're just going to go on a little journey here real quick and find out what the current value for r is. So at this very instant, my calculus is finished, right? All that blue stuff's done. So I'm fair to now work on my transient values. At that very instant, the x squared would be what, 0.8 squared plus 0.6 squared for the y is equal to r squared. And when I tried that out, I had a nice, beautiful exact value of 1 mile. So I think we're ready to go. Now, there's one spot in here where a lot of students make a small little error. So I'm going to actually make the error first, and then we'll fix it. So I'm going to substitute values in. The x. This is the current transient value for the speeder's distance from the intersection, 0.8. The dx dt, that's what we're looking for. That's our goal, is to find that. Plus the y. Where's the police car? How far away? And we're told it's 0.6 away. And then the dy dt, okay, well that's the police car's velocity there, right? So, okay, 60 equals the current r value, 1. And then the dr dt, how fast is that radar saying the distance is changing? And it says it's increasing at 20 miles per hour. So I'm going to go down here and say, yep, it's growing at 20 miles per hour. And this is not right, and it will actually give you the wrong answer because of one little issue. The police car right now is driving towards the intersection. It's getting closer and closer, and the value for y is getting tinier and tinier. Now, I know they were kind and said, oh yeah, the police car is moving at 60 miles per hour, but that's actually how fast the value for y is getting tinier. So you have to go in here and read the story carefully, and you have to put in a negative, okay, because you've got a decreasing y. Right now you've got them driving away at 60 miles per hour. Right now we want them driving towards the intersection. Once you've done that, then everything just falls into place and you find out that dx dt, this would be a velocity, it's the velocity of the speeding car, is a positive going away from the intersection 70 miles per hour. Okay, and that's going to finish up this lesson for today. So the whole idea with this lesson for today is you have multiple things changing and it's no big deal. Write down some equation that relates all the letters together and then just take a time derivative.